So, hello everyone. Today I'll be talking about a project where we try to relate white matter measures to cognition and cardiovascular health. So, as we age, unfortunately, our brain deteriorates, and that is also true of white matter. And it is thought that some of these white matter deterioration could be contributing the age-related cognitive decline that is commonly seen, specifically in processing speed and fluid intelligence. However, there have been quite a lot of studies, but they often use very different measures of white matter, which makes it difficult to compare across them. Also, studies often use relatively small sample sizes in very limited age ranges, such as like having only 20 young adults versus 20 old adults, which sometimes makes difficult to make generalizable conclusions. So just to give you an example of the number of different white matter measures people can use, there's a lot. I'm not going to go into detail in all of them, but like I have arbitrarily grouped them here into common measures that you might get from a typical T1 image, such as just the volume of the white matter. Some people, especially in the clinic, use white matter lesions that are, for example, due to cardiovascular disease. There is a magnetization transfer ratio that is a bit older sequence, often used in multiple sclerosis. More recently, people have started using this as part of a pre-processing of just like the ratio of a T1 and T2 weighted imaging. However, in research, people often are nowadays using diffusion-based measures of white matter integrity, but even there, you have quite a lot of different measures of white matter. The most common one is fractional anisotropy, but there's also mean signal diffusivity, mean signal kurtosis, NODI, and all kinds of different measures. The diffusion ones are basically based on water diffusion in the brain and are tried to be a bit more specific to white matter, whereas the clinical and common are supposedly measuring some of myelination, but also might be capturing certain other aspects. So here I would just like to point out this measure, which is the peak skeletonized mean diffusivity. So mean diffusivity is just how much diffusion there is in a certain voxel. And this slightly newer measure is asking within the white matter tracts, what is the range across the whole brain of white matter tracts for these diffusivity values. And this is quite simple to compute and relatively novel measure that has been linked to white matter damage in microstructural damage and small vessel disease in the brain. So the good thing about our cohort, the CAMCAN, is that we have about 600 people, and we had quite a lot of these different white matter measures. So we could examine how are these different white matter measures related, how they change with age, and do they relate to cognition and other factors. So in this project, we used 7 diffusion metrics, mainly the fractional isotropy in all in white matter tracts, mean signal diffusivity, kurtosis, NODI, which is neurite density, orientation dispersion, and free water content. And we also used the PSMD-like measure of just the variance of MSD across the white matter tracts. We also have the magnetization transfer ratio and the T1, T2 ratio, and also white matter lesions. So we computed all of these measures across the white matter tract, but then averaged them so that we have a single value per measure per participant. And we performed fact analysis on all of these 11 different white matter measures. So just to show you how the descriptive statistics of these values, basically here you can see that most of these measures change with age. Some tend to decline, such as fractional isotropy and neuronal density, which are thought to reflect health of white matter tracts and somewhat myelination. Some increase with age, such as the mean signal diffusivity, the free water, and the lesions. And here you can see the correlation matrix showing that a lot of these measures tend to be capturing quite similar information. Specifically, we have one block of values between free water content, white matter lesions, and diffusivity and variance of the diffusivity being highly correlated, whereas some of the other measures, again, being clustered but showing slightly more lower correlations, with probably the orientation dispersion and white matter volume being the least correlated. So when we performed fact analysis on all these measures to try to summarize them and basically gain less measures that would then reduce the number of multiple comparisons people have to do if they are trying to find the best measure to relate for their specific research question, we used element-wise cross-validation and found that 4 factors tended to capture 90% of the variance in the data. So 4 factors was enough to capture these 11 measures. And we saw that they captured somewhat intuitive white matter factors, such as factor 1 tended to decline with age and captured fractional isotropy and neuron density and negatively on diffusion. So we refer to this as a factor capturing microstructural properties, myelination, and white matter integrity. On the other hand, factor 2 captured mostly measures related to free water content, or I refer to it often later in the talk as the white matter damage factor, because it loads quite a bit on white matter lesions as well as free water content and high diffusion. And basically, if you have a lesion, you often have a bit more water in the white matter, therefore leading to more free water content and diffusion. We have one factor basically mainly capturing the orientation dispersion index that doesn't really change that much with age. It shows a U shape. And factor 4, which mainly captures the kurtosis signal, which is measuring the non-diffusion aspect of the diffusion metric. So it's basically capturing the heterogeneity in the tissue, and it's therefore we name this factor white matter complexity. And it also loads positively on white matter volume. So you can think of it as white matter complexity, and again, another white matter health aspect. And this factor also doesn't change that strongly with age. So I've shown you how to partition some variance in white matter factors, but I haven't shown you whether this is particularly useful. So to examine this, we try to test whether these white matter factors relate to other biological and cognitive factors. Specifically, we were interested in cardiovascular health because cardiovascular health is one of the biggest risk factors for dementia and lower cognition in old age. And a lot of the previous work has linked cardiovascular problems with white matter damage. And also some previous work in the CAMCAN has shown that, again, we have quite a few cardiovascular measures. And these cardiovascular measures can be summarized in 3 latent factors, similarly to how I just showed you with the white matter measures. So for example, here the the cardiovascular latent factors. One factor might be representing just static blood pressure and BMI. Another captures the pulse pressure. So this is the difference between systolic and diastolic blood pressure and has recently gained popularity as a measure of cardiovascular health. And another captures heart rate variability. So when we relate our cardiovascular health factors to our white matter factors, regressing out for age and sex effects, we see that there was a direct path between the pulse pressure factor and our white matter factor 2 that represented white matter damage or free water content, which we think makes intuitive sense, such that if you have lower cardiovascular health, you would have problems with your white matter. But because we work in the cognition and brain sciences unit, we also wanted to look at cognition. So we related in a separate analysis how these white matter factors predict cognition over and above age. And we see unique contribution of the different white matter factors, such as that fluid intelligence was predicted by our 2 white matter health factors, the one that was capturing white matter integrity and the one capturing white matter complexity. And interestingly, we saw different factors predicting processing speed, a different measure of cognition that is often linked to how much myelination you have in the brain to be quicker on simple reaction time tasks. So I know you might be thinking, well, what if I don't have 12 white matter measures? How do I pick a single white matter measures for my next study if I'm designing especially a cohort study? So here we examined for each individual white matter measure how it relates to age and different cognitive measures. And you can see there is quite a lot of heterogeneity with MSD, so PSMD variance being the highest age variable, showing the strongest relationship with age. However, mean signal kurtosis was the one when you were trying to predict fluid intelligence. And the best measure when you're trying to predict processing speed was fractional anisotropy. So there is heterogeneity depending on the type of question you're trying to address. However, if we are making recommendation, we would think that the PSMD-like or MSD variance is the most sensible because it shows the strongest relationship with age, relatively good relationship with fluid intelligence, and relatively good relationship with processing speed. And it is also relatively easy measure to compute from other cohorts, whereas kurtosis, for example, that is the best for fluid intelligence, might not be available in other cohorts. So with that, I'll summarize. Basically, we've shown that we can summarize different white matter measures in simply 4, we think, relatively interpretable white matter factors. I've shown that pulse pressure tends to relate to free water content or white matter damage across lifespan sample. I've shown you that different types of white matter factors seems to relate to different types of cognitive measures, making it important to pick your white matter measures depending on the research questions you have. And if you're picking a single white matter measure, it might be that PSMD-like measures, such as variance of mean signal diffusivity, may be a good capture-all measure that is a good starting point. And with that, I would like to thank my collaborators, Marta, Rafael, Kamen, and Rick Hansen, and you for listening. Thank you very much.